Hello and welcome back to Math Class in Session. Today, a little bit of physics and a little bit of math. Vocabulary and background. Forces such as wind speed, water currents, power generated by airplane engines, gravity, acting on a mass are all represented as vectors in math calculations. From elementary physics, force equals mass times acceleration. The units of force will have to be mass units multiplied by acceleration units, so kilograms times meters per second per second. Kilogram meters per second is one of those is called a Newton. That's the units of force, newtons, kilogram meters per second per second. Acceleration due to gravity would be the force acting on a single kilogram, and that would be 9.8 meters per second, or 9.8 newtons. So the force acting on a kilogram, pulling it towards the Earth, is 9.8 newtons. That's really the part you need to remember. It's just our conversion factor from kilograms to newtons. It's 9.8. Resultant, as we proceed with more vocabulary, resultant of forces is a single force which, when acting alone, would have the same effect as all the other forces combined. So it's really the sum of all the forces. And calculating that sum is called composition of forces. Equilibrant is the exact opposite of resultant. It's a single force that undoes or counteracts the effect of the resultant. And it turns out that this is always the negative of the resultant. So if the equilibrant is present in a system, you won't see any motion. It's like a tug of war. One team's pulling in one direction, the other team's equally pulling in the exact opposite direction. There might be forces, but there's no movement. This is called a state of equilibrium. When three vectors, as opposed to a tug of war with teams pulling along a line, so the forces are collinear. If three vectors are in a state of equilibrium, they're not collinear, they're coplanar, and they form a triangle with a vector sum of 0. So if we had vector A and vector B, two forces acting on an object, the resultant would be the sum, A plus B, but the equilibrant would be the exact opposite of the sum. That would be vector C. And you'll notice that A plus B plus C is 0. C is the equilibrant, and the net force acting is 0. So there's no motion. It's a state of equilibrium. Notice how the three vectors not only add to 0, but they are in fact coplanar. Example, two forces acting on an object, 35 newtons and 50 newtons, and they're pulling on this object at an angle of 30 degrees to each other. Determine the resultant and the equilibrant of the two forces. Here we have our object here. One force pulling in this direction at 35 newtons and another force pulling in this direction at 50 newtons, and there's an angle between those two forces of 30 degrees. To calculate the resultant, we add vectors. So it looks like the parallelogram method would be good. Let's make the parallelogram and draw in the resultant. So these two vectors together are making this blue. It's as if there was just this blue line pulling on an object located here. And that's called the resultant. Now let's observe. It is a parallelogram. The lines are parallels. So if there's 30 degrees here, we have to understand, we have to know that there must be 150 degrees there, because these two add to 180. And if it is a parallelogram, the opposite sides are equal. So if this is 50 newtons, this must also be 50 newtons. And I'd like you to get ready for a whole lot of cosine law and sine law, because that comes up a lot for a little while. Here we'll use the cosine law. R squared, or the magnitude of R squared, equals 35 squared plus 50 squared minus 2 times 35 times 50 times the cosine of 150. And that will give us the magnitude of the resultant. which is 82.2 newtons. And I'd like to know at what angle it's pulling in relation to the other two forces. So let's call this angle theta, a Greek letter often used to denote an angle. And let's work out theta. Now that we know this is 82.2 newtons, we're going to use the sine law. So it'll be sine theta over 50 equals sine 150 over 82.2. And so we got theta. Theta is 17.7 degrees. And we know what the other one is as well, because altogether it was 30 degrees, so the other one must be 12.3. There we have it, the situation with the resultant. We know its magnitude, we know its direction in relation to the other forces. Let's consider the equilibrant, which is the exact opposite of the resultant. It's got the same magnitude, and it's like a tug of war. It's pulling the exact opposite direction. And we can get the angles that it associated with the equilibrant just by considering the supplements of 17.7 and 12.3, because they have to add up to 180. Another example, a plane flying at a certain speed, say 200 kilometers an hour on a heading of 065. Resolve the motion into northerly and easterly components. Now we have to understand 065 means we head straight north and then bend clockwise 65 degrees. So 65 degrees is down here. And I didn't put it there, I put 25 here. The complement of 65. 65 plus 25 is 90. And this would be a component pulling easterly. And this would be, let's call that force in the x direction. And this would be a component pulling northerly. And we can call that force in the y direction if you like. And so we can resolve this 200 or express this 200 as a force in the east towards the east and a force towards the north. That results in this 200. And we can see that the cosine of 25 is adjacent over hypotenuse. So the force in the x direction is 200 cos 25, which is 181.3. And we can see that the force in the y direction is equal to, well, let's see. Sine of 25 is opposite over hypotenuse. And if we multiply by 200, we get 200 sine 25. And so the force in the y direction would be that number. And so this 200 could be expressed as 181.3 kilometers an hour to the east and 84.5 kilometers an hour towards the north. It's taking a vector and expressing it as a sum using trig, SOHCAHTOA. Now, this diagram is so important that I wish to make it into a general case. When we have a right-angled triangle, the side, one of the components, in this case the force in the x direction, one of the components is a multiple of the hypotenuse. Now the hypotenuse is the longest side, and a sine and a cos is a number slightly less than 1, we know from grade 11 math. So to get the force in the x direction, we'll take the force and multiply it by, in this case, the cosine of theta. So Force in the x direction is big F times the cosine of theta. Why cos? Because this is adjacent to the hypotenuse, or adjacent to theta. So adjacent over hypotenuse. While this one, the force in the y direction, will be the hypotenuse force times the sine of theta, because it's the opposite side. A good little diagram to remember. Comes up a lot. Do you want this? Force times cos theta. Did you want this? Force times sine theta. Example, a television weighing 15 kilograms, suspended from 2 wires, attached to the ceiling at a couple of angles, 35 degrees and 60 degrees. Calculate the tension in the wires. We'll use composition of forces, and we'll make a position diagram, which is simply a diagram. It's a diagram of reality. This is a TV, this is a wire, this is a wire, this is a weight on the TV, it's a force pulling down 15 kilograms. Reality as we would see it with our eyes. Then we're going to draw this thing called a vector diagram, which means that we're going to draw these vectors over here in a triangle. Now, any vector I draw has to be parallel. I'll start with wire 1 here and draw a vector parallel to that. Then I'm going to draw a vector parallel to wire 2, but I'm going to attach it to the end of wire 1. And now this is a straight up and down vertical vector with an arrowhead on the bottom, so I'll draw that here, straight up and down with an arrowhead on the bottom. So I harvested out 3 vectors from a position diagram into a triangle of vectors called a vector diagram. It's a triangle of vectors from the position diagram. Now the tricky part is to put angles inside this vector diagram. To do that, let's consider between wire 1 and the vertical, what's that angle? Well, there's wire 1, and there's the vertical. Whoops, wait a second. That's 147 newtons because it's 15 times 9.8. That's where this 147 comes from. It's 15 times 9.8. Now, where were we? The angle between wire 1 and the vertical. Well, there's the vertical. And the angle between wire 1 and the vertical, we can see here, is 30 degrees. So we'll put a 30 there. Next, between the vertical and wire 2, well, there's the vertical and there's wire 2. The angle here is the complement of 35. And that's 55. And that leaves a certain number here, which will be the result of adding these two together and subtracting it from 180 degrees. And let's just do that. It's 85. So this will be 95. And so this is useful because now we can use a sine law. Didn't I say lots of sine laws and cos laws? So we can use the sine law here. The force in wire 2, W2 over sine 30 equals 147 over sine 95. Click, 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 and we've got wire 2. I didn't show the work. I just put the answers down. So use the sine law, and it's simple to determine wire 1 and wire 2. Just use the sine law, and there they are. By the way, don't take my word for it. Actually do that. Now we're going to do this a completely different way. It's the same exact question. We're going to use a different method. It's going to have the same position diagram, except for now we're going to do the following. The plan is to resolve the forces. So this force on wire 1, we're going to resolve it. Just like we did with the plane flying, it's partly to the east and partly to the north. We're going to resolve it into vertical and horizontal components. And the key to finding the tension in the wires is that the vertical ups must equal the vertical downs, and the horizontal rights must equal the horizontal lefts. That would be 2 equations in the 2 unknowns. So I made a big diagram, and we're going to take the force that's pulling on this wire and resolve it into its two components. One's pulling to the right and one's pulling up. And we're going to use that special case I talked about to put an expression here. This is the hypotenuse. Because this is a Z pattern, there's a 60 here. And so I can say right away that this must be W1 cos 60. Similarly here, using our general case, this must be W1 sine 60. Resolving this one into left and up, right here, right away, I can say it must be W2 cos of 35, because 35 is also located in this corner because of the Z. So this must be W2 cos 35. While this must be W2 sine 35. Now we'll just say, okay, this is 15 kilograms. It's still 147 newtons pulling straight down. So the ups equals the downs, and the rights equals the lefts. There's a left, there's a right. There's an up, and there's a down. So let's see, the ups equals the downs. W2 sine 35 plus W1 sine 60 must equal 147. And the left must equal the right. W2 cos 35 must equal W1 cos 60. And now we've got two equations and two unknowns. So hopefully I don't need to explain how to solve that. I did it by substitution instead of elimination. Isolated W2, turned it into a decimal, subbed it into the first equation. Kept on working by turning this into a decimal. Collected like terms, divided through, got W1, substituted it back, and I got W2. The same as before, of course. Quick review of what we've done here. We've done a single question, and we did it in two ways. First, we did it by using a vector diagram where we transferred the three vectors and made a triangle and worked hard to put the angles in it, and then just used a sine law. It's one way to do it. It's called composition of forces. And the other way we did it was we resolved the forces into one's pulling right and pulling up, and this one's pulling left and pulling up, resolved it into left and right components, left and up and down components, and ups equals downs and rights equals lefts. So that's another way to do the same problem. Two equations and two unknowns. Lastly, is it possible for three forces with those magnitudes, 10 newtons, 27 newtons, and 15 newtons, to be in equilibrium? Answer, no. Reason, because there's a law for triangles. In any triangle, no one side can be greater than the sum of the other two. Think about it. The two endpoints of 27. How could we join them with the distances 10 and 15? You can't get from one point 27 units away. So if one is larger than the sum of the other two, you can't have those forces in equilibrium. I've included a couple of questions that represent challenges. The second one is basically the TV hanging where you're not given the weight of it, but you are given the tension in the wires. And I've included the answer to that one. These might be worth your time, if you got any time. I know that people are busy. Thanks for listening and have a great night.